Dr. Brian Williams, and I'm going to talk about the economics portion of this project. We had two main objectives for the economics portion of this project. First, we determined the net present value of an on-farm water storage system over a period of 25 years. Second, we determined the feasibility of irrigating from an on-farm water storage system when compared to the alternative of rain-fed production with no irrigation at all. To conduct this study, we needed to collect information on the study site as well as price, yield, and weather data. The study site was described earlier by Dr. Taggart. We collected two crop prices, the projected baseline prices from the Food and Ag Policy and Research Center at the University of Missouri, as well as futures prices. We also collected yields from Noxubee County, available from the Risk Management Agency. Weather was collected from a PRISM data set, and the budgets were created using Mississippi State University's 2016 planning budgets. In addition to looking at the study site mentioned earlier, we looked at two other alternative scenarios that will likely be typical of an East Mississippi producer. Among those scenarios, we look at an 80-acre field and a 160-acre field. The 80-acre field was assumed to have a quarter-mile-long center pivot that made a half circle, while the 160-acre field has a quarter-mile center pivot that makes a full circle. The size of the reservoir was scaled down accordingly so that the reservoir-to-field size ratio was proportionate to that of the study site. Once all of the data was collected and the scenarios were created, enterprise budgets were constructed that assume a 50-50 corn and soybean rotation. The 2016 Mississippi State University planning budgets were used to estimate the production costs of each crop, as well as the cost of operating the center pivot irrigation system. It is nearly impossible to predict markets, yields, or even weather several years into the future. One solution is to simulate these variables to create a distribution of expected outcomes. To simulate prices, we started with the projected prices released by FAPRI based out of the University of Missouri. These estimates are often used by legislators when analyzing policy impacts. We use historical futures price volatilities in combination with the FAPRI projected prices to simulate prices for this project. Yield, precipitation, and the average growing season temperature are simulated from detrended Mississippi yield data and historical Mississippi weather data, while also taking care that yields are also correlated with weather. In other words, if there is a hot, dry summer, that will be reflected by lower yields. Once our yields, prices, and weather have been simulated, those values are used to calculate a 25-year simulated annual net returns represented the 25-year useful lifespan of the on-farm water storage system. Each year's net return is then used to calculate the accumulated net present value for those 25 years. We also incorporate an interest rate to account for the time value of money. By doing this, we are giving more weight or importance to the outcomes in the early years and less weight to the outcomes in the later years. This whole process is repeated 1,000 times to create a distribution of net present values representing a range of possible outcomes from investing in an on-farm water storage system. We also looked at two different scenarios with respect to how the on-farm water storage system was funded. The first is assuming the system is paid for in full upfront. The second is assuming the system was financed over a period of 10 years with a 5% interest rate. This is a snapshot of the average yields, temperatures, and precipitation from our simulation. They are representative of the conditions that would have been seen in eastern Mississippi. Moving on to our results, this is a table of the results from an 80-acre field with the system paid for up front. We looked at several different scenarios, including 3 discount rates and 5 crop insurance coverage levels, ranging from no insurance at all to an 85% coverage rate. As you can see in this table, in an 80-acre field, rain-fed is almost always more profitable than irrigation with an on-farm water storage system. There are several reasons for this, but the biggest driver is that on an 80-acre field, one would have to pay for the full cost of a center pivot, but those costs would be spread over fewer acres since that center pivot is only making a half circle. Moving on to a 160-acre field, we see similar results when we use an upfront payment. However, the gap between irrigated and rain-fed values are much smaller. Something else worth noting in this table is that the range of outcomes is much smaller for irrigated production than for rain-fed production. In other words, irrigated production is much less risky. For example, looking at a 4% discount rate, the minimum loss is $67 for irrigated acres compared to a loss of $350 for rain-fed. So the downside risk is much smaller. Moving on to the 488-acre field representing the study sites, we saw similar results when the costs of the on-farm water storage system are paid for upfront. This indicates that at least when the costs are paid for upfront, the returns from investing in an on-farm water storage system are lower than the alternative of relying on rainfall. However, an on-farm water storage system is still profitable with all of these values remaining positive for the net present value. It also does reduce risk. Moving on to a net present value when the system is financed over 10 years on a 160-acre field, we see the results change a little bit. We begin to see the differences narrow even more. In one case, at an 85% coverage rate, the on-farm water storage is more profitable than relying on rain-fed production. Delaying the payment of on-farm water storage systems into future years can take advantage of the concept that money is worth more now than it is in the future. To break these results down into a graph and give a visual representation of how the outcomes of installing one of these systems will work, we have a graph of a cumulative distribution function, so a range of all of the outcomes at a 6% discount rate on an 80-acre field when the costs are paid for upfront. Notice the group of lines to the right are all of the rain-fed alternatives, while the group of the lines to the left are their alternatives with the on-farm water storage system. In other words, rain-fed does seem to be more profitable. However, that distribution or those lines are spread out more than with the irrigated system. When we look at the 160-acre field, we see similar results. However, all of the lines become closer together. In this case, the rain-fed alternatives are still higher on the upside, but they come and converge on the downside. So it means that there's more or less risk, but less upside potential on the on-farm water storage system. Finally, here is a graph of all of the outcomes from the simulation using a 160-acre field where on-farm water storage system costs are financed over 10 years. In this case, rain-fed alternatives still have more upside potential, but the gap closes even further. The range of outcomes for on-farm water storage also become much steeper. This indicates that while on-farm water storage does have less upside potential, as with previous graphs, it also comes with much less risk and more consistency than the rain-fed alternatives. So far, it seems that in most cases, rain-fed production is still slightly more profitable than constructing an on-farm water storage system. But as Dr. Taggart alluded to earlier, an on-farm water storage system brings value in other ways besides simply providing an irrigation water source. An on-farm water storage system also captures nutrients, sediment, and chemicals that would have otherwise ended up in our river system and ultimately in the Gulf of Mexico, contributing to the hypoxia problem there. Because of these added benefits, there's already a program in place in many Delta counties where the NRCS will help producers to cover the construction costs of an on-farm water storage system. With that in mind, we incorporated a what-if scenario into our analysis and looked at the potential outcomes if a producer would receive a 20% and a 40% cost share allowance for the construction of the on-farm water storage system. Here are some of the results for when a 20 and 40% cost share are included on a 160-acre field with the cost of the system paid for up front. At lower discount rates, on-farm water storage becomes more profitable than rain-fed in several scenarios. Next, we looked at the same situation with the on-farm water storage financed over a period of 10 years. Here are some of the results when a 20 and 40% cost share are included. Under all but the highest discount rate, a cost share program helps to make an on-farm water storage system feasible when compared to relying on rainfall. Overall, the feasibility of an on-farm water storage system relies upon the scenario that is used. First, field size matters. Constructing an on-farm water storage system and the accompanying center pivot irrigation system is a significant investment, and the more acres that investment can be spread over, the better. This lowers the per acre cost of the system and increases the system's efficiency. It is also better to take a loan out for the system than it is to try to pay for the cost of the system up front. Much of this comes down to the idea that more now is better, and spreading the costs well into the future means that they will be discounted. On a similar note, lower discount rates are better, but the discount rate is dependent upon what the alternative investments will look like. If the only alternative is putting money into a savings account, then the discount rate will be low to reflect the returns from that savings account. Alternatively, if the alternative is investing in the stock market and receiving a rate of return close to 10%, then the discount rate will be closer to 10%. Additionally, a cost share program makes a significant difference in the feasibility of an on-farm water storage system by reducing the upfront cost of installing the system without reducing any benefits from the system. Finally, we found that when used in combination with crop insurance, on-farm water storage systems are an excellent risk management tool. Even in scenarios where the average profitability of an on-farm water storage system is lower than that of rain-fed production, the variability in income is dramatically reduced, particularly when it comes to limiting downside risk. Oftentimes, in economics, we can call this a risk premium. In other words, producers sometimes are willing to pay or receive slightly lower profits to remove that downside risk. I'd like to take a moment to thank the farmers that allowed us to use their field as a study site, Mr. Dale Weaver and Mr. Paul Good. We would also like to thank Dr. Dennis Reginelli, and we would like to thank the Mississippi Soybean Promotion Board for funding this project.